Hello everyone. I hope you guys had a great Easter, and we are now going to start our second day of class notes on 8.5. So our main focus today, as you can see in all of these examples, is to be dividing radicals. We're going to work to divide radicals. First example, a lot of times, again, the directions will say to simplify. So fourth root of 125. 125 is not perfect. And I don't think any of those would go into 125 evenly. So I'm going to look at, can I reduce 3 over 125? So I'm going to try to reduce 3 over 125. And that doesn't reduce either. So then my goal is to get the radical out of the bottom. So think about what fourth root I need to multiply by to make this perfect. So it looks like I'm going to have to get to 625. So I'm going to take 625 and divide it by 125 and see that that means I have to multiply it by 5. So the fourth root of 5, because then 125 times 5 will give us that perfect fourth. So I'm going to end up with the 2 on the outside, the fourth root of 3 times 5, which is 15, over the fourth root of 625. And now this is perfect. It will come out. 15 can't be simplified, so I keep the 2 times the fourth root of 15 over 5. The numbers outside cannot reduce. Final answer. I only have a cube root in the bottom. I have a number on the outside that I'm going to ignore and a number in the numerator that I'm going to ignore. My goal is to rationalize to get rid of that cube root in the bottom. So I have to make that perfect. Well, with a 5, looking at how am I going to get to one of these numbers, and I'm going to assume it's probably going to be 125. So again, I'm going to take 125 and divide it by 5. And see that I get 25. So I'm going to use the cube root of 25. Multiplying by the cube root of 25 will give me 5 times 25 is the 125, and that's a perfect. So we get negative 5 times the cube root of 25 over 2 times the cube root of 125. 125 comes out as 5. With the 2 and the 5 that will come out, we multiply to get 10. And then my numbers outside this time can reduce. 5 goes into 10 twice. So I end up with negative cube root of 25 over 2. Final answer. Rationalizing the denominator still simplifying, guys, is still part of simplifying. So my directions here could also be to simplify. But I put this in from chapter 12. You should remember conjugates. So conjugates, if we have a plus bi, its conjugate is a minus bi. And we used conjugates with imaginary to get rid of the imaginary pieces. We use conjugates with radicals to get rid of roots in the bottom. When you have two roots separated by addition or subtraction, you have to use the conjugate to get the roots out of the bottom. Rationalizing the denominator means no roots in the bottom. So for this example, actually I'm going to go to this example first because it's a little less complex than that one, but it's the same thing. I have one root in the bottom, but it's being added with the 3. It's not being multiplied. So because of the addition, that's what makes this problem more challenging. That tells me, because of the addition being in the bottom, that I have to use a conjugate. If I multiply by the conjugate, it should get rid of the root in the bottom. So the conjugate of 3 plus root 6 is 3 minus root 6. We do that to the top and bottom, just like we do when we want to rationalize here. So 2 times this quantity, it's just distributing. So we get 6 minus 2 root 6. So 3 times 2, 6 minus 2 root 6 in the top. In the bottom, when we use conjugates, I always like conjugates because I can see that this is just a sum and difference pattern. So instead of like FOILing or distributing and multiplying all of those terms, I could just use the pattern. Square the first, square the last, and put difference in between. Square the first, we get 9. Square the last, we get 6. We put subtraction in between. The top's going to stay 6 minus 2 root 6 over 9 minus 6 is 3. Now here, you can't simplify here because all 3 numbers outside would have to be able to simplify. And you'll see that when we do this problem here. But all 3 of these values, in order to simplify, kind of like factoring out if these had something in common like the 2, you could factor out the 2, but then you'd see like the 2 and the 3 would not simplify. So final answer here. Going back to this one and using conjugates. So if I have root 2 minus root 7, I'm going to put parentheses around this because this is considered a binomial as well. Conjugate's going to be root 2 plus root 7, root 2 plus root 7. I can't use a pattern here because they're all different, so I'm just going to go ahead and distribute. Root 3 times root 2 is root 6. Root 3 times root 7 is root 21. Root 5 times root 2 is root 10. And root 5 times root 7 is root 35. All over. Now I can pattern here because I have my difference, sum and difference of squares. So I can use, I have sum and difference, so I can use the difference of squares pattern. Difference of squares to square the first, so we get 2. Square the last, we get 7, and put subtraction in between. None of these are like, and when I think of perfect squares, and if there's a perfect square that goes into 6, the answer is no. 21, no. 10 can't be simplified, and 35 can't be simplified. So all of those, we can't add them together because they're not like, and we can't simplify them, so they just all stay the same. So my top just stays the same, and 2 minus 7 is a negative 5. Final answer. No more root in the bottom. We tried to simplify, we tried to combine any like radicals, and we can't. So, next example. This is different because this is one root, not 2 separate like this one. So, still a root in the bottom that we have to rationalize. We have to get this out of the bottom. We have to get this root out of the bottom. And so what we do is we just multiply by the entire root. We multiply by the entire root. And then we just have in the top x times root x minus 6. In the bottom, we have the square root of x minus 6. We have 2 of them. So you can see that this would get rid of the root in the bottom because squared and a root cancel each other out, leaving me with x times the square root of x minus 6 over x minus 6. Now you can't cancel those out again because of the subtraction. So that's how we leave our final answer. No more root in the bottom. Simplifying this one, we need to work to simplify this. Find the perfect square that goes into 32. That's going to be 16, biggest perfect square. I'm going to leave the 2x outside. I'm going to write this as 16 times 2, and x squared is perfect as well. I'm going to leave that over 6x. So I get 2x. 16 is perfect. It comes out as 4. And x squared is perfect. It comes out as x. So this comes out as x, and this comes out as 4. That's why I have a 4x outside. This came out, I'm left with the root 2 underneath. All over 6x. And so like I was talking about in this one, we can't reduce because they all don't have something in common. But in this one, we can reduce because these 3 things have something in common. We can reduce, we can divide a 2x. When we divide by 2x, we get 1. We divide by 2x, we get 2. When we divide by 2x, we get 3. So my final answer ends up being 1 plus 2x root 2 all over 3. Oops. And that's our class notes for today. Bye, everyone.